Good evening, my name is Xuecheng Xun, and I'm going to present the paper Semantic Guidance of Dialogue Generation with Reinforcement Learning. The other co-author is Ma Weiyun. Nowadays, deep learning has gained popularity in dialogue generation, but its black box-like nature makes it difficult to control. In addition, dialogue generation based on maximum likelihood estimation may result in responses that are irrelevant to the given post. So, in this paper, we came up with an idea to introduce semantic guidance to gain better control of the generated context, and we focused on single-turn dialogue generation. We hope that the generated response will follow the given semantic guidance and also will be correlated to the given post. While implementing current methods to meet our goal, we face some difficulties. The first is that when giving semantic guidance to dialogue generation, the assigned semantic may be repeated or absent. In addition, since the major goal of model is to meet semantic restrictions, the generated response may be dual or unrelated to the given post. To solve the first problem, we implemented reinforcement learning and a specially designed recording system to ensure the desired semantic appears exactly once and does not repeat. As for the second problem, we implemented conditional GAN to ensure the generated response would be diverse and also related to the given post. Let's dive deeper into the detailed methods. We mentioned semantic guidance earlier, but what is the proper semantic guidance? In this paper, we arranged synonyms of a certain keyword as semantic guidance. These synonyms were drawn from a knowledge network like EHALNet. For example, if we want the generated response to include a concept like tribe, we can find the synonym words ethnic group, and clan in EHALNet. These synonyms are then arranged as synonym set or synset and work as semantic guidance in this paper. Later, we tried to incorporate synset into dialogue generation. We implemented semantic condition LSTM, which was proposed by Wen et al. In 2015. An extra vector DT was introduced to the original LSTM to record the information of the assigned dialogue act in the original paper, and we used it to record the assigned synonyms. However, the vector DT still does not guarantee that the desired semantics will appear exactly once, and also, there is no record on the appearance of desired semantics during generation steps. To perform a dynamic recording of desired semantic, we implement an extra dialogue act record cell, or DAR cell. An extra one-hot vector XD is introduced to record the present status of the assigned synonym set during generation process. What should be noticed is that DT records all the synonyms, but SD records only synonym sets because we only want one of the synonym in the same set to appear. Then, how is the vector SD updated? In the beginning of the response generation, we select a certain synonym set and find its corresponding synonyms in D0, which is used to record the information of the assigned synonyms. We also initialize SD as a series of zeros. While generating the response, if any of the synonym appears, we updated the corresponding synonym set in SD. For example, we want the generated sequence to include tribe, and when the word tribe appears at the second generation step, S2 will be updated to have a 1 in the vector. The 1 corresponds to the synonym set of tribe. Now we only record the status of the desired synonym set, but still have not guaranteed it to appear exactly once, and we will fix it later. Up till now, the generated response still lacks diversity and correlation to the given post, so we try to implement sequence scan, which was proposed by Yu et al. In 2017. The sequence scan uses Monte Carlo search and a discriminator to give a score to each generated word during generation steps. The scores then serve as reward for reinforcement learning, which helps the generator to generate sequences that can achieve higher scores. We hope our generated sequence can include the desired semantics and does not repeat. Also, the sequence has to be correlated to the pose. Therefore, we change the scoring formula of the original sequence scan. The scoring formula now includes rewards from the sense counter and also a discriminator. The sense counter has the following formula and will be maximized when the desired sense only appears once. As for the discriminator, it contains two LSTM networks and judges the correlation of pose and response by reading the pose and response in different orders. The final hidden state of the two LSTM networks will then be used to generate reward value of the discriminator. After summing up the reward value from both discriminator and sense counter, the total reward will be implemented in reinforcement learning. Finally, we have achieved our goal to ensure that the desired syntax will appear exactly once, and also the generated response will be diverse and correlated to the given post. Now let's come to the experiment part. In this paper, we chose Weibo conversational data. There were 570,000 post-response pairs for training data and 2,000 pairs for testing data. The testing data was separated to two parts. The first part used semantics that were randomly fetched from real responses to exclude the influence of semantic selection, and was used in both human and automatic evaluation. The second part uses semantics that were randomly fetched from posts to test the feasibility of model in practical scenario, and was used in automatic evaluation. And we chose several methods as baselines for comparison. These baseline models can be modified to incorporate semantic information into sequence generation. We chose sequence-to-sequence with attention, hierarchical gated fusion unit, and semantically conditioned LSTM as baselines, and SER LSTM with reinforcement learning as our proposed method. In the first part of the experiment, we implemented human evaluation to judge the fluency and relatedness of our generated responses. Here we follow the settings of Sean et al. In 2015, which categorized the responses into suitable, neutral, and unsuitable levels, each with score ranging from 2 to 0 points. And we can see in Table 1 that our proposed method receives the highest score. And we also compare our method with HAFU, which has the second highest score. It turns out that our method also wins with a higher percentage. We also evaluate how our model helps reduce semantic repetition and absence. It turns out that our proposed model with reinforcement learning reaches the lowest semantic repetition and absence rate. We can also notice that SIGDIAL with overgeneration has low semantic repeating and absence percentage, but it gets lower score in human evaluation. Here we also try to evaluate the influence of discriminator in our method. So we have a model trained with discriminator and another without discriminator. It turns out that a model without discriminator can focus more on reducing repeating and absence of semantics during generation, but the generated sequences are less diverse and also shorter. To automatically evaluate the diversity of our method, we adopt the design of Li et al. In 2016 by introducing unigram, bigram, and trigram. The higher the different grams, the more diverse the generated sequences are. We can state that SELSTM with overgeneration reaches highest diversity, but the diversity is because the generation process is by random selection in this method. And our proposed methods reached great diversity in this evaluation. What should be noticed is that by comparing methods with and without discriminator, we can find that discriminator brings greater diversity to response generation. We also looked up our generated results and found that our proposed method with discriminator generates the most suitable response. In sequence-to-sequence methods, there is no semantic guidance given, and we can say that the generated result is not so fluent. We also can find that with discriminator, the generated response is more diverse and related to the post. Since our semantic guidance is given in synonym set, we hope that when given a synonym set, it can use different words in the sequence generation. And in the example below, we can find that although we choose a certain keyword from a post, it does not directly use the exact keyword in response generation. Instead, it uses the synonyms of the keyword in response generation. In conclusion, we propose SER-LSTM with reinforcement learning to ensure that our desired semantics only appear once and do not repeat. We also implemented conditional GAN and found that it helped generate more diverse response. Our proposed model also outperforms other baseline methods in human evaluation and achieves lowest repetition and absence of given semantics in generated responses. As for the selection of semantics, we leave it in future work.
Hi everyone, my name is Siqi. Today I'm here to introduce our work on counseling style reflection generation using generative pre-trained transformers with augmented context. In the recent years, there has been an increasing demand for counseling services in the States. According to a report from Mental Health America, there are more than 10 million adults in need of mental health treatment. It failed to get the resources they need, and the number has not declined since 2011. The main reason for the unmet need is that we don't have enough mental health workforce. With a decreasing number of physicians in psychiatry and the time-consuming clinician training process, we seek to leverage this problem with the help of modern NLP techniques. Reflexive listening is an essential skill for a clinician to acquire, if not the most important, and has been shown to lead to positive outcomes. Therefore, our work mainly focused on generating responses that show reflexive listening skill. The previous works of using NLP in counseling domain are mainly in these three facets. Some of the works investigate whether certain characteristics contribute to a good counseling, such as the length or the sentiment of the response. Other works solve the problem of automatic coding, which also provides a global feedback to the counselor. But all these works only tell the counselor what to do, not how to do. And by generating a response, the counselor will get the chance to learn what can be some plausible responses. In our work, we proposed a system that takes the dialogue context as input and produce a reflexive response as output. The right-hand side illustrates what reflections might look like. According to William Miller, the founder of motivational interviewing, a reflection can be classified to be either a simple reflection or a complex reflection, where a simple reflection repeats the content with some wording, and complex reflection will make a guess about meaning beyond the context. We design our system following these guidelines. Our system is built in a modular way, which allows the generator to take additional input from other modules to get more context. And here's the overall workflow of the system. Since available annotated data is scarce in counseling domain, we built our system based on a pre-trained language model. On the upper side, it's a component to get a reworded version of the client's utterance. And on the lower side, it's a component for retrieving responses from similar dialogue context. I'll explain the components in more detail in the following slides. A pre-trained language model makes it possible to build a working system with relatively limited amount of data. We choose GPT-2 from OpenAI as our base model, since it's an autoregressive language model that's able to do text generation. It is composed by stacking self-attention layers and feed-forward layers, in which the self-attention is masked based on causality. Based on some preliminary experiment, we choose to use 5 previous utterances from both counselor and the client as the dialogue context. For the sake of simplicity, GPT-2 is also used in the classifier. To provide additional context for the generation, and as a strategy used by counselor to avoid the sense of repeating, we construct a worded version of client utterance with the process shown on the right side. Firstly, we look at the utterances from the client and use part of speech tagging to select out the essential words, including verbs and nouns. We filter out the high-frequency common words and also stop words. For the remained words, we perform a lemmatization. For example, grandchildren becomes grandchild, and wanting becomes want. We then use the lemmatized form to look up their synonyms in the WordsNet, which is an external lexicon database for English. Lastly, we randomly sample one word from multiple synonyms to replace the original word, and provide it to the generator as an augmented input. The retrieval module is based on the intuition that if in the past there were clients talking about the same issue as the current session, it may be helpful to check how did the counselor respond at that time. The retrieval module does this in a two-stage way. The first stage is matching previous session from transcript database with the current dialogue context based on TF-IDF. This step narrows down the response candidates. Then, all counselor responses candidates from the relevant sessions will be paired with the current dialogue context and check how well do they match by a classifier. The top candidate will be used as an augmented context for the generation model. The classifier is another neural model based on GPT-2, and it is trained to give a matching score for a context-response pair, with the assumption that the responses produced by counselor are good matches to their context. On the right side is an example of input. As a common practice, augment context from retrieved response, content expansion, and dialogue context are concatenated to form a sequential input for the transformer model. Since the self-attention mechanism is ignorant of tokens order, a positional embedding is used to encoding the ordinal information of the input sequence. We also use an additional type embedding to indicate whether a token is from augmented context, client, or the therapist. All three inputs shown here will be mapped into the corresponding embeddings by 3 different embedding metrics. All the embeddings are added and feed into the transformer model. In this example, we got the dialogue context where the client said, "I had a really hard time sticking to my diet this week," where sticking and diet are underlined, since they are essential words we found. They are then replaced by their synonyms adhere and dietary. And with the retrieval module, we can find some plausible responses. In this case, you're wondering whether you will be able to lose weight this way, which was also about weight management. And with all the information from the input, the target of the generator is to give a response, such as, you are wondering whether you'll be able to adhere to a diet. We use 2 different datasets to train our model. The Alexander Street dataset contains counseling transcript of different styles and on various topics. Since it's not annotated, we used it to train the model with language modeling objective as a domain shift. The main dataset we used is composed of more than 250 motivational interviewing sessions, focusing on behavioral change. For the automatic evaluation, we use several different metrics. The top 3 metrics are different versions of Rouge, and they are all counting the word overlap. We show that by enforcing the important words with synonym content expansion, the model achieved the highest score in all n-gram-based metrics. That in the middle are metrics based on word-to-vec embedding. Here we used embedding pre-trained on Google News corpus. Instead of matching the exact words, it focused more on the similarity in semantics. From the result, it is shown that response retrieval lead to outputs that are semantically closer to ground truth by offering an alternative response found in the database. Since a higher score in automatic metrics doesn't necessarily mean a better output, We further validate the efficiency of our model with human evaluation. We built an interface where the annotators are asked to give a score to a response given the dialogue context. To ensure a fair comparison, the annotators do not know whether the response is ground truth or which system the response is from. We used 3 different criteria, where the relevance measures whether the response is on topic, and reflection likeness measures whether it follows the guideline for reflection, and the quality measures whether it is fluent and without grammatical error. The result shows that all the models based on pre-trained GPT-2 models significantly outperform the baseline. It is also shown that the model is able to generate better outputs using additional context from the retrieval and the content expansion approach. And the model achieved a score similar to the ground truth on all 3 metrics. Here's an example from our system. Although not as detailed as the ground truth, our model all produce relevant and fluent responses. In this example, by enforcing the important words in the context, the model with content expansion gave a more specific detailed response with mentioning the client's concern about the future. As a conclusion, we have built a model that generates counseling reflections and have improved the model with techniques inspired by counseling guidelines. Experimental results, including automatic metrics and human evaluations, both show that the model benefits from the retrieval and content expansion method, and it is able to produce responses showing reflexive listening skill. If you want to know more about our research on motivational interviewing, please visit our website. Thanks.
Hi, my name is Lena, and I'll be presenting my paper, Learning from Mistakes, Combining Ontologies via Self-Training for Dialogue Generation. We know that creating NLG data-to-text datasets is labor-intensive and time-consuming, but new attributes are constantly being added to databases. We want to be able to reuse and combine data from existing ontologies and their associated training data to create new utterances. Here is an example. Let's say we have one ontology and training data called NYC, and we want to be able to generate combined utterances which have attributes from not only NYC, but also another data set and ontology, E2E. We would then create a meaning representation, or MR, with attributes from both sources that we dub combined or COM. While these data sets do have some unique attributes, they also have some in common, like the 2 in this example, which are shown in orange. That the names for area and location are different is not important since they realize the same information, and mapping can trivially fix this. NYC has a dialogue act that E2E does not have, and 3 attributes that are not in E2E's ontology. These are represented in red. E2E also has 3 attributes in blue in this example that are not used in NYC's ontology. When we combine the ontologies together, we can create new MRs that have attributes from both original ontologies. In row 3, we can see that there are all 3 types of attributes in the combined test MR. We then want to be able to generate an utterance that contains attributes from both ontologies, especially the attributes unique to a single ontology, which are represented in red and blue. An example utterance is in the last column of the 3rd row. Our paper makes 3 main contributions: the definition of a generation task for generating from unseen MRs that combine attributes from 2 datasets with different ontologies, systematic experiment on methods for conditioning NLG models, and a novel self-training method that learns from the model's mistakes. First, I will go over ontology merging a bit more. There is first one source of data, NYC, with its ontology. Our example has 2 types of dialogue acts and 7 attributes. We then have a second source of data, E2E, with a different ontology, which has 1 dialogue act and 8 attributes. Because they are in the same domain, there are 4 attributes that overlap. We can then combine the ontologies together after merging and relabeling attributes to create 1 large ontology with 2 dialogue acts and 11 attributes. Our data comes from two sources in the restaurant domain, the E2E Generation Challenge and the NYC dataset. The training data is balanced over the two datasets, resulting in a dataset of about 77,000. We then manually create a test set with 3,040 MRs, where every MR combines attributes from each dataset, and half the test instances utilize the Recommend Dialog Act. The lengths of the MRs are normally distributed between 3 to 10 attributes. Also, since this is a new ontology, there are no gold standard references to compare to in test, since the whole point is this data doesn't exist and we had to create this test set ourselves. Our model architecture is represented on the right. It is a standard RNN encoder-decoder model with 3 types of side constraints as model supervision, also called conditioning, 2 which are input to the encoder and 1 to the decoder, to represent which source the data comes from. Here is a more in-depth look at the model supervision. First, we have the no sup, where there is no additional source supervision. Then we have the adder supervision, where the source information is appended to every attribute. Next, we have the bool supervision, where the source information is in a new attribute. And finally, we have the guide supervision, where the source information is inserted directly into the decoder. I will now describe our text-to-meaning semantic extractor. We create this for 2 reasons. First, we don't have gold references, making automatic evaluation using methods such as BLUE impossible, so we need to be able to determine the semantics in the utterance automatically for evaluation. Also, we need to retrofit MRs for self-training. I will go over our self-training regime in more detail later. Our method is a rule-based automatic aligner that tags each output utterance with the attributes and values it realizes. We have an example on the right. We can see that the original MR and the output don't match. While there are a good number of attributes that are properly realized, represented in orange, there is an extra value not in the original MR, represented in green, and 4 attributes in the MR that are not in the output. We can modify the original MR to create an MR using the text-to-MR extractor that removes the attributes from the MR which are not in the output and inserts the attributes in the output that are not in the MR to create a new and accurate MR. And a similar approach for automatic evaluation has been used in previous work. We have 3 types of evaluation metrics. First, we have the slot error rate. This calculates the semantic error by using the text-to-meaning semantic extractor to determine the number of the 4 types of semantic errors which can be present in utterances, and normalizing them by the number of slots in the input MR. We also have the perfect percentage evaluation metric, which is the percentage of outputs that perfectly match the input MR. And finally, we have the human evaluation on naturalness, coherence, and grammaticality. Here are our model's initial results. We can see from these results overall that this is quite a challenging task because none of these results are very good. In fact, the perfect percentage is below 6% for all models. Of the 4 models, adder has the most perfect utterances, though no sup and bool also do comparable. Guide does surprisingly poorly, and we will therefore not include it in the rest of the experiments. We also perform human evaluation to determine if these results are at all natural, coherent, or grammatical. We can see that the human evaluation, which is only done on semantically perfect utterances and therefore must have some combining of ontologies, is quite good, indicating that we do have utterances we can potentially work with. So how can we make this work? We decided to try self-training. We need a couple of things to attempt self-training. We need perfect outputs, so the MR matches the utterance that combine attributes from both sources to add back into training. And we need outputs that are natural, coherent, and grammatical. From the human evaluation, we know that we have the latter, but our initial model results indicated that we have very few perfect outputs. But this can be resolved using the text-to-meaning semantic extractor to retrofit corrected MRs. As we showed earlier, by taking an original MR and an output, we can generate a fixed MR, which is shown here as the text-to-MR. That has the corrected attributes and values, and therefore can be considered perfect. But we don't just need perfect outputs, we need ones that combine attributes from both sources. We define a new metric, source blending, that counts the number of combined outputs. This graph unpacks these previous results according to the length of MR and source blending results. We can see that there is a significant number of source blended utterances, much more than the 5.5% of perfect utterances in our initial best model. We can also see that the Boole model has the most source blended utterances, making it a potential best option as the model supervision for self-training. We also need to remember that half of our test set includes recommendation dialogue acts. So we also need a model that can produce recommendations. Boole not only has the most source blended utterances, but also has the most source blended utterances with the recommend dialogue act. This cements our decision to continue with the Boole model for self-training. For our self-training experiments, we start with the 77,000 training examples and then add back in 1,405 retrofit MR-NLG outputs from the Boole model. We experiment with two types of self-training regimes, S-repeat, which keeps repetitions and adds them back into self-training, and S-unique, which only adds unique outputs back into self-training. Here are our self-training results over 10 iterations, where the perfect percentage goes up considerably, reaching 82.9% for S-repeat, a 77.4% absolute improvement over our initial results. Our slot error rate also drops to close to 0 with our S-repeat model. Since the COM test set was used during self-training, we construct a new test set using the same procedure as before, called COM2, and test it on the final iteration of our models across different MR lengths. We can see that while these results vary across MR length, they are comparable to COM, and we therefore know that the trained model generalizes to new test sets. Here we compare the results of S-repeat, our best model, with the results of Boole, the initial model for self-training, to highlight the difference from before and after self-training. While perfect percentage at longer MR lengths are 0% for our initial model, they are over 50% for every MR length after self-training. Here are some example outputs from the self-trained model, where we can see a number of aggregation methods are used to combine attributes from both sources, not just concatenating the separate sentences. For example, in the first row, we can see the recommend dialogue act from NYC is combined in the same sentence with the E2E attributes, family friendly, and eat type. In the second row, the NYC and E2E attributes are joined using a with operator, and in row 3, there is a single sentence with 4 attributes. The NYC attribute is preceded and followed by the E2E attribute with the reverse in the last row. In conclusion, these are the first experiments on training an NLG for an extended domain ontology by reusing existing within domain training data. We show that this task is surprisingly adversarial and that self-training methods results in high-quality, natural, coherent, and grammatical outputs with high semantic accuracy. In future work, we plan to generalize to combine 2 distinct domains and possibly improve self-training with additional referenceless evaluation metrics. Thanks.
Hello, welcome to my presentation. I'm glad you could join. My name is Michael Heck, and I present recent work that we did here at Heinrich Heine University. The title is TRIPPY, a triple copy strategy for value-independent neural dialogue state tracking. Let me start by putting this work into perspective. Task-oriented dialogue systems just recently gained widespread acceptance with personal assistants in many homes and on many smartphones. This popularity demands robust and scalable solutions for multi-domain settings, such as the one that we see here on the side, since assistants are expected to be useful for a wide variety of tasks. And also for open vocabulary settings, since more often than not, vocabularies cannot be predefined. This talk is about a particular component of dialogue systems, the dialog state tracker. Systems rely on dialog state tracking to monitor the goals of the user throughout the course of a dialogue. To fulfill a user goal, the dialog system must extract relevant information from the user input and track this information during conversation. Here's an example to explain the task at hand. In order to recommend a restaurant to a user, the system needs to know preferences in terms of price, location, and so on. To do that, the system maintains a dialog state. The dialog state is the summary of the conversation until the current turn. It forms a set of constraints, usually in the form of slot value pairs. Slots are concepts that the user can talk about with the system, and values are instances of those concepts. Some examples you see here in the table. Tracking the dialog state is essential for the system to pick its next action. Domains, slots, values, and actions are usually defined by an ontology, and traditionally, ontologies were fixed and prediction was performed over all slot value pairs. These pick list-based approaches perform well on small data sets, but they have some scaling issues. They require a complete ontology, for instance, by including all possible booking options. But this is not sustainable for real-world applications. Recently, span-based approaches to DST gained popularity. These methods directly extract values from the dialog context. Transformer architectures, such as BERT, generate contextual representations that are especially useful for this task. The downside is that span prediction only suits values that can be found in the input directly. These methods also struggle with natural language phenomena, such as co-references and implicit choice. Lastly, recent hybrid approaches improve the flexibility when handling variance in expressions, but they have the same scaling issues as picklist-based methods. Scalability and generalization is linked to an idea called value independence. It is desired that the dialog state tracker's performance is independent from which values it knows from training or from picklists. Looking at recent approaches, there seems to be a trade-off between the level of value independence and dialog state tracking performance. Ultimately, none of the recent approaches are value independent in the strict sense. They are either limited by the capabilities of the applied methods, or they have scaling issues. In order to address these issues and improve value independence, we propose TRIPI, Triple Copy Strategy DST. TRIPI is a hybrid approach that avoids the scaling issues of other hybrid approaches. Our model relies on span prediction to extract values directly from user input whenever possible. In addition to that, two copy mechanisms can copy values from memories that are maintained on the fly. TRIPI does not use any predefined pick lists and uses the dialog context as the only source of information. The model decides for every slot which copy mechanism to use. The inform memory tracks values that were informed by the system. If the model predicts that a value was informed, then the value is copied from the inform memory. This solves the implicit choice issue. The dialog state memory tracks previously seen values. If the model predicts that a value was previously assigned to another slot, then the value is copied from the dialog state memory. This solves the co-reference or the value sharing issue. I would like to walk you through the model design step by step. There are various tasks that the model has to solve. For each turn, the dialog context needs to be encoded. This is done by the context encoder. The encoder takes as input the current user utterance, the previous system utterance, and the dialog history. The output of the encoder is one sequence representation and a sequence of token representations. Once the context is encoded, the model needs to do the following. For each slot, predict whether a slot value is present in the input or not. This is done by slot gates. Then the values need to be copied into the dialog state. This is done by either span prediction or by using the memory mechanisms. Slot gates determine whether a slot is present in the current turn. They predict none if the slot does not take a value in this turn. Don't care is predicted if any value seems acceptable. Otherwise, the slot gate predicts span if the value can be extracted via span prediction. Inform if the user refers to a value that was uttered by the system, or refer if the user refers to a value that is already assigned to a different slot. Boolean slots have separate slot gates. Span-based value prediction works as follows. For each token, the model computes its likelihood to be either the start or the end position of a span. Then the most likely start and end positions among all tokens are picked. A slot is filled by an informed value stored in the informed memory, if the user positively refers to it, for instance by confirming a choice that the system offered, like in the example here. And if span prediction cannot be used, that is, if the user only did an implicit choice and there is no span to extract. Slot gates can predict that the user refers to a value that has already been assigned to a different slot during the conversation. Another classification head then predicts the slot which contains the referenced value. The value of that slot is copied to the current slot. This can also happen across multiple turns. We mask the values and past system utterances to force the model to focus on the historical context rather than specific values. The slot gates also use auxiliary features. These are binary vectors that indicate which slots were recently informed and which slots were already filled before. I will now talk about the experimental evaluation. We tested TRIPPY on 4 datasets. Multi-WAS is the most complex dataset. The challenge here is the multi-domain setting and the large ontology. WAS is a standard benchmark. And SIM-M and SIM-R are interesting because some of their slots have a high out-of-vocabulary rate during testing. For comparisons to other methods, we use joint goal accuracy. This is the ratio of turns with correct slot value assignments, including empty slots. During training, we also fine-tune BERT. We use an input length of 180, except for multi-WAS, where we use the maximum. The figure on the left compares TRIPPY with recent methods that also tested on multi-WAS. The figures on the right show the performance on the single domain datasets. At the time of submitting this work, our model achieved state-of-the-art performance on all 4 datasets. Most notably, we pushed the performance on the demanding multi-WAS by another 2% absolute. The consistent improvements on all datasets demonstrate that the model generalizes well to multiple domains. SumBT, for instance, performs very well on WAS, but falls back on multi-WAS. TRIPPY scales well with the data. SIM-M has less than 400 training examples, but TRIPPY maintains performance better than, for instance, BERT. Our approach is also robust to OOV values. LUDST performs well on SIM-R with a moderate OOV rate, but struggles with the extremely high OOV rate on SIM-M. I will come back to the issue of OOV values again shortly. We conducted an ablation study to find out how the individual components contribute to the performance of TRIPPY. Our baseline model is best compared to BERT-DST, which only takes single turns as input and only uses span prediction. The low performance shows that the dialogues in multi-WAS are too complex for a single copy method. Applying the triple copy mechanism improved performance greatly, especially the slot gate performance. This modification also enables resolution of co-references, even across multiple terms. We found that historical context is important to reduce ambiguity so that values are assigned to the correct slots more often. Adding the auxiliary features proved to be complementary to the dialogue history. The additional information about the current progress supports the slot gates. Partial masking only resulted in minor but consistent improvements across datasets, and using the full input width is obviously of advantage for longer dialogues like the ones that we see in multi-WAS. We wanted to make sure that our model generalizes well to unseen values. In the figure, you see the slot gate, and span prediction accuracies for slots with exceptionally high OOV rates. We compared their performance to the average performance for all slots in the respective datasets. We found that the slots that expect named entities generally perform worse, but the OOV rate does not seem to be the main cause for this. For instance, even at a rate of 100%, the movie slot of SimM still performs comparably well. To confirm that, we did another test. Here you see the recall of values depending on how many samples for each value we see during training. Surprisingly, OOV values are detected just as well as generally less common values. We found that TRIPPY generalizes better over the number of seen training samples than the baseline does. Lastly, we did an extreme test where we replaced most values in the multiverse test set with OOVs. On the right-hand side, you see the per slot accuracy on the original test set and on the OOV test set. What can be seen is that most slots maintain a high accuracy. We took this as proof that TRIPPY has a good OOV handling regardless of the slot type. Let me summarize this talk. We have seen that TRIPPY handles challenging DST scenarios. Unseen values during evaluation do not generally impair performance. And the memory-based copy mechanisms improve robustness and generalization, as the model is less affected by data sparsity and is not limited by a predefined vocabulary. In the future, we would like to investigate slot independence. We also plan to incorporate a better dialogue state update strategy. I thank you for your time, and I'm looking forward to see you at the Q&A.
Hello, can anyone hear me?
Yes, yes.
Yes.
Cool. Nice to see you guys. Do we have everyone here?
Sean, if you give me, I'm gonna do one thing really quick.
Sure. Are we live now? To see you guys.
We are live, but I'm gonna show.
We have everyone.
I did want everyone to see,
Sean, if you give
how
me
to join this meeting. You can join it this way, if you can hear me all right. So here's the Trello card. If you go to session 1, generation and task-oriented dialogue, and scroll to the very bottom, you have live QA. And you click on that, you can join the live QA, and I will let people in. I did want everyone to see,
Sean, if you give
how to join this meeting. You can join it this way, if you can hear me all right. So Sean, I guess you're in charge now.
Cool. I think we're still missing an author, right? A speaker. Chen Xuan, Xie Chen Xuan. Cool. I think that's give the speaker another like 2 minutes. I think we officially started in 2 minutes time. Cool. Is Xie Chengsheng or Ma Weiyun in the meeting? Because they are the first paper to do the live QA. Okay, if they are not here yet, I think that we can start with Shigi maybe. So yeah, welcome everyone. So this is a very new format of running a conference. I guess this is like first time for everyone. This is also my first time as well. So we'll see how it goes. So in total in this session, we have 25 minutes and we have 4 papers to go through a live QA. So each paper would have around like 5 to 6 minutes time. So I will try to keep at that roughly about that time. So then, you know, if you have any questions for a particular paper that, you know, you can type it in the chat or, you know, just like, you know, I don't exactly know the raise hand functionality, but, you know, just like cue me. So I will let you ask a question. Yeah. Cool. So I think that Xie Chengsheng is in the meeting now, right?
Yep.
Should we start with you? So is there any questions for the first paper, the semantic guidance of dialogue generation with reinforcement learning? Anyone in the meeting room wants to ask any questions? Cool. If no one in the meeting room has question yet, I have prepared a few quick questions to ask. So first things that I want to ask Chengsheng is, so in the method, it seems like you use a very similar architecture to SCL/STM, and have you tried to use reinforcement learning to train a lab model and comparing to the tool as well? So I know that, you know, in your proposed model is a very different architecture, but then on top of that, you have reinforcement learning trained on top of that. But because due to the RL training objective seems to be outperforming the previous models, but have you tried to use the same training criteria on low baseline model as well, just to do a fair comparison?
Actually, I didn't try to use RL on other models. The model without RL is called the SCR model. I use a maximum likelihood method to train the SCR model, and I found that SCR model without reinforced learning already has outperformed other baseline models like HGFU in reducing repetition or absence of semantic in experiment. So that's why I use reinforcement learning only on the SCR model.
Okay, but you know, I remember in your table, you know, maybe I am wrong, but you know, in your table, it seems like when you're comparing to SCL/CTM, you know, it seems like the performance is not better, right? If you didn't train it with reinforcement learning.
It is okay with human evaluation, but it is not shown in the table. But what matters is that the SCR/LSTM without reinforcement learning has still more repetition or absence of semantics compared to with reinforcement learning. But still, it is still better than other baseline models like HGFU or SCL/STM. Yeah.
Okay, cool. Any questions on this paper? So I have another quick one. So it's related to the statistical significance on the human evaluation. Have you done any like calculations on that? Is the result significant?
Yeah, but I think that's important, but I did not really do it in this experiment. So yeah, I think that is what I can do in future work.
Cool. Okay. And since these approaches actually trying to compare into a lot of different diversified models. So have you tried to compare to like more baseline models, rather than just sequence to sequence model, but also like GPT based model and things like that?
Yeah, I think that will be cool, but because like GPT is like a trend now. I think comparing to GPT or maybe implementing reinforcement learning on GPT may be something that can be done in the future.
Cool. Okay, sounds good. Does anyone have any questions? Would be very welcome to ask any questions if you have any. We have only one last question left for this one. Cool. If not, then we can move on to the next paper. So the second paper is Shiki Shen. The paper is about counseling style reflection generation using generative pre-trained transformers with augmented context. So does anyone have any questions on this paper that you want to ask the author? No?
I see Barbara has a raise.
Barbara has her hand up.
Oh, cool. Okay. Barbara, please.
Hi, this is Barbara Di Eugenio from University of Illinois at Chicago. I wanted to ask, with respect to the human evaluation, it went by a bit fast, but from what I understood, while there were differences among the systems, the error bar showed that there was no real winner. So that was, from the examples you showed, especially, the one that didn't have anything to do with the answer, with the original comment by the person, and the answer by the system, it seemed that there was some real difference. So do you have any thoughts about that?
Hey, thanks for asking. And firstly, in the chart, our system based on pre-trained language model beat the sec-to-sec model with significant, statistical significance, but the improved version of the model doesn't have a statistical significant improvement over the merely fine-tuned version. So that's the first point. And for the human evaluation, what I get is a question. You have some question on whether the system is.
Can I rephrase? So from that graph, it seemed like the error bars. You had 3 human evaluations, and it seemed that the error bars for every version of the system were not. There was no real statistical difference on the human evaluation. So I was just curious if you have any thoughts about that.
Yeah, I admit we have a lot of things to improve on the human evaluation. We have a fairly low inter-annotator agreement, as we mentioned in the paper also. So we might improve on like the annotators training process in the future work.
Thank you.
Cool. I have a very quick follow-up questions on that as well. So it's also about the human evaluation. So who are those judges that to do this human evaluation? Are they like experts in that particular domain, or they are basically people you hired from Amazon, Mturk, or any sort of crowdsourcing platforms?
It was some member in the lab who's undergraduate student and graduate student, but with no background knowledge on motivational interviewing.
Okay, Cool. And then what is the size of the pool? Like how many people evaluate on
We
that?
had 4 annotators.
Okay, only 4. Okay. Cool. Do we have any other questions around this work? If you have any question, just feel free to speak up. Yeah, I think all the people are muted here, so should be fine. No? If not, I have another quick question is regarding to the baseline. So it seems that you're only comparing to the sequence to sequence baseline, but that model was quite a long time ago. That was in like 2014 or something. Have you think about like comparing to more like latest models?
Yes, we've had considered that, like including HRED, things like that. In my thought, we can kind of think the fine-tuned version as a baseline. We expect that to outperform the previous model, as we've seen in many cases. And so our contribution will be in the improved techniques that provide augmented context to the previous fine-tuned only model.
Okay. Cool. I think we are ready to move on to the next paper. So the next paper's author is Lena Reed, and the paper is Learning from Mistakes, Combining Ontologies via Self-Training for Dialogue Generation. So anyone in the room wants to ask Lena any questions about her work?
I see Michael there has his hand up.
Cool.
Hey, can I jump in? Hi, Mike White from Ohio State and Facebook. Thanks a lot for the talk. That was very clear, very nice idea. Well done. One thing I just wanted to ask about, right? So, you know, it's been very common to re-rank outputs by semantic correctness, including from your team's entry into the E2E. So the strategy you took was when, during the self-training, was when you generated an output that wasn't correct, you changed the MR, which makes sense. And it's like what Kedzie and McEwen did. But I'm wondering if you also looked at re-ranking the outputs and picking the one that, you know, trying to find correct outputs out of an best list and using that in the self-training. Was that something you looked into, or what are your thoughts on that?
Yeah, no, I don't think it was something that we actually thought of. That's interesting though, because we only had very few that met our criteria to begin with. So sort of taking all of the ones that were that worked was necessary to have enough for self-training. So, you know, the perfect percentage was tiny. If we'd only added those in, the accurate ones, we wouldn't have had enough to really start the self-training process.
But that was the perfect ones, was like the single best output that was correct, right? Did you look further down and best list or something like that?
No, because we wanted to make sure that the MRs were correct so that the model didn't learn to generate from MRs to generate hallucinations or deletions. So making sure that those MRs matched was important in our mind.
And did you use re-ranking in your final experiments, or always just went with the single best in the end? We
went with the single best. Yeah, we went with the single best for the entire time. We didn't do re-ranking. It's something definitely we could consider though, to try to get more outputs that could have helped us get more outputs for sure.
Okay, great. Well, thanks a lot. Thanks again for a great talk.
Cool. Any other follow-up questions for Lena, or any new questions as well? Cool. If not, I have also a few questions around that. I think that, this is a very interesting work, and I really like it. I'm just curious about, seems like the experiments that was done on two different data sets and try to merge them into one. Have you thought about build up a gold standard data set to evaluate what is the upper bound of the performance would look like, so that you can see that how far you are still from from collecting the actual data set for that joint domain.
So to create a data set that has both
in
it?
Yeah, and then it's created by humans and actually labeled by humans, so that you have a gold standard for that.
For training? Yeah, that sounds really interesting. I would take a lot of manpower and work to do,
exactly, yeah.
Which is a big reason why we don't have gold. I think it could be a really interesting way to figure out what the best results look like. Because like you said, we don't have that upper bound. We don't have what would be the best generated data with these combined MRs. And yeah, I think that could be a really great way to do that. We just haven't considered it because we just don't have the resources to do that.
Yeah, I think maybe a very quick way to do that is take one of the existing data sets you try, and then try to manually split them into two subdomains. And then, then in that case, you have a joint ones and also two subdomain ones. But then, in that case, all the training data in each of the domains will be much less. So, there will be probably some challenges around that. But at least you will be able to establish a gold standard metric somehow.
Yeah, I mean, you could try to do some automatic combinations that then someone maybe manually fixes. Especially if you were combining separate sentences, those tend to combine more easily. Only issue is then you'll have a data set with too many separate sentences. So maybe humans doing some manual combination as well could fix data and make it a little easier without having to,
So Sean, Barbara's hand is up again.
Oh, okay. Barbara, do you want to ask a question? Cool.
Yes. So maybe I just didn't understand it from the talk. It went fast. I was curious about your aggregation that you showed in those examples at the end.
Mm-hmm.
Done, end-to-end fashion, or was it a post-processing, or?
For those final examples?
Yeah, like you showed how, you had different attribute with combined from the different sources combined with, or in one case, it was a completely different sentence. I mean, a junk clause, if I remember, and things like that. So.
But was the question, how did we get that? Sorry.
Yeah, or I mean, the question was there a specific module devoted to particularly aggregation, or was it just part of the general architecture?
Oh, it's just part of the general architecture. We found those as sort of particularly interesting examples to show how the model could do this aggregation and doesn't just concatenate separate sentences, which would fulfill, the brief, but be less interesting.
Thank you.
Yeah.
Cool. Any other questions for Lena's work? Cool. If not, we can move on to Michael's work then. So the next paper that we are going to discuss is TriPi, a triple copy strategy for value-independent neural dialogue state tracking, work done by Michael. Does anyone have questions that you want to raise now?
Michael, you're unmuted. Does that mean you have a question?
No, I'm me. Yeah, I'm happy to answer any question.
Yeah. So, yeah. go on if you have a question. All right, I have one. So it seems like the model is an interpolation between three different kind of mechanisms, right? And it's learned by the neural network model. Is there a way, or have you tried to visualize, like how okay, not how important is it, but whenever there's a prediction that is going to be made, which part of the model can actually contribute the most to that prediction? Have you tried any kind of visualizations around that? Because I thought that would be very interesting to see.
I'm not sure if I fully understand.
So, for example, So for example, in a particular dialogue scenario, like when you try to predict the next the dialogue state, for example, which part of the model actually contributes most? Like, for example, whether it's like a value, like the span extraction part of the model, or is it like a copy part of the model? Is there any way that you can visualize it in your model?
I cannot think of any way to visualize it, but you can compute the statistics. So we have those three copy mechanisms because those cover probably almost all the cases that we see in those data sets, how values can be expressed by the user. And by far the most common mechanism that the model uses is the span prediction, because most often the values are just expressed explicitly. But you see in our numbers that having those additional copy mechanisms is outperforming those methods that only rely on the span prediction. And the reason is that there is a considerable amount of values that are that constitute co-references, and values that were informed by the system and that have been referred to implicitly by the user. And those mechanisms, of course, they capture those cases, and that was not possible before.
Okay, that's cool. Yeah. Another quick follow-up question from me is that you mentioned about the context. Maybe I'm just not fully aware of the work, but how does the context fit into the model? Are they represented by structured dialogue state, or you just fed a sequence of sentences from the history?
Yeah, we do two things. We have the dialogue history added to the input of the encoder, which is one way to add the context. And the other way is it's a very simplified version of the dialogue state and the inform memory. It's two binary vectors that tell the model which slots have been talked about in the past, either by the system or by the user. And those two types of context, they were complementary. So in the beginning, we only added the history to the encoder, and then we found that if we add those binary vectors, that also helps. And it's just intuitively, it just helps the model to distinguish or to make a better decision in ambiguous cases. So if the user says something like, I would like to purchase a ticket, and it could be a bus or it could be a train. And if you have the dialogue history, hopefully there is some information that right now the dialogue is about train, and then the model can make a more reliable prediction.
Cool. Okay. Sounds good. So, does anyone have any questions for Michael?
I actually did have a quick question. I didn't want to be first. Is it pronounced tripy or trippy?
It's pronounced trippy, yes, but it's a bit confusing.
Very good.
We call it trippy because it's also implemented in Python. So.
Okay.
Oh, I see.
Yeah.
It's my natural instinct to go with Py because I use Python every day. So. Any other questions from the audience here before I take all the time asking Michael questions?
I do have one question. How did you find is the standard deviation or the variability in training times and model prediction? I'm just wondering about nonlinearity in the model, and what's the variance in between training rounds, and how many epochs did you usually took to train?
Oh, okay. Well, we took a rather conservative learning rate, so convergence is a bit slower. And I think I set the maximum number of epochs to 20, and sometimes it reached those. So we had an early stopping mechanism in place, and sometimes it reached the 20 epochs, and sometimes it didn't. But it was never best after only 10 epochs or something like that. So I can say that about the epochs. We did not really have a detailed look about the variance there. For the performance, it's because it is a rather conservative learning rate. I have the numbers actually in the paper. On multi-was, it's less than 0.3% absolute in standard deviation on the joint call accuracy. So that's actually rather stable.
Okay, cool. Thank you.
Yeah.
Cool. Thanks, Michael. So I guess this concludes today's Q&A section. And thanks everyone for joining, and hope you guys all enjoy the rest of the conference.
Thank you, Sean.
No
I'll
worries.
I'll take it from here for just a moment. There are a couple of things I would like to show you. This is really big. So on the Trello board, I wanted to show you a couple of things. We have a news card. If there's news that we want everyone to know about, you can, of course, go ahead and click on that and look at the news. But I also wanted to show you that you can watch a card. So if you click on this and scroll down a little bit lower, hopefully you can see this. You can click on watch, and watch just means if there's any changes to the card, if anyone adds comments, it will have a notification on that card right here. So you can see that there's something new there. And that I would recommend doing that for these four cards, excuse me, the news card, the conference day 1, conference day 2, and conference day 3, because there will be updates to the YouTube links. So, but you can do that for any card you'd like. The next thing I want to explain is how the demo session is going to play out. It's a little bit confusing, but I think you'll benefit from a little bit of an explanation. If you go to session 2 demo, this is happening right now. In fact, we're running a little bit late. There are 5 things happening simultaneously. If you go to the bottom of that list and click on this card right here, live interactive meetings, there are 4 links to Zoom meetings for each of the 4 papers. So if you're interested in asking the authors about their demo, they can show you. Go ahead and follow one of those links and join them. It's kind of like a virtual poster session almost, but it's demo. Obviously, you can come and go in these different Zoom conversations that are happening. Meanwhile, in this live stream, we're going to be playing the pre-recorded videos, the pre-recorded presentations. So if you aren't sure which one to join, you can at least be watching this. These will be playing during the entire time that these meetings are happening. But if you feel so inclined, please join one of them and ask the authors different questions. We hope that the authors are in those meetings right now, ready to go for you to join and start asking questions. With that, I'm going to start the pre-recorded videos for the demo session.
Casey,
anyone who is
yes, could you show again where are those Zoom links? Sorry, I couldn't see.
Which links now? Those links, if you go to the Trello board, you go to session 2 demo 1, scroll to the very bottom. There is the live interactive meetings card.
All right, in the very bottom.
There.
Cool.
Yep.
Thank you so much.
Just like, and that's how it's going to be for all live QA. It's at the bottom of or underneath at least all the cards. And anyone who is still in this Zoom meeting, I'm going to kick you out as I start the, go ahead and leave in the nicest possible way. But then I'm going to start the next part, which are the demos.
Hello, I am Weronika Sieńska, and I would like to present recent work that I have done together with my colleagues from the Interaction Lab at Heriot-Watt University in Edinburgh. I am going to demonstrate how our system works right after this short introduction. The title of our paper is Conversational Agents for Intelligent Buildings, and I'll start with a brief description of the conversational agent that we've developed. In our project, we used a social bot called Alana, which had originally been created at our university for the Amazon. Hello, I am Weronika Sieńska, and I would like to present recent work that I have done together with my colleagues from the Interaction Lab at Heriot-Watt University in Edinburgh. I am going to demonstrate how our system works right after this short introduction. The title of our paper is Conversational Agents for Intelligent Buildings, and I'll start with a brief description of the conversational agent that we've developed. In our project, we used a social bot called Alana, which had originally been created at our university for the Amazon Alexa Prize competition in 2017 and then 2018. Both times it reached the finals. It offers open domain social chat about various topics such as movies, sports, politics, and technology. On the right-hand side, you can see several examples of user utterances. A user can choose what they want to talk about, and they can also ask questions about Alana's views, likes, and dislikes, such as what its favorite movie is. Alana can also provide its users with current news that is retrieved from many different news feeds. It retrieves data from sources such as Wikipedia and Reddit, and therefore is capable of chatting about, for example, the CEO of Microsoft or Joni Mitchell. Now, Alana successfully serves as a system core for other conversational AI projects at Heriot-Watt University. One of them is the Grid project, where we adapted Alana to a research building called The Grid, where it acts as a host. You can see the building in the picture on the right. Alana is deployed as a Google action and therefore is available on Android phones with Google Assistant, but also on several Google Home Mini smart speakers distributed in the Grid building. We have recently deployed it on a Furhat robot as well, and can easily deploy it on Telegram in the text mode. The adaptation of Alana to the Grid building consisted in adding several new functionalities. In the Grid project, Alana tells the visitors where particular rooms are and how to get to them. And for that, it uses a topological map of the building. It offers information regarding events happening in the building, which is retrieved from an online calendar for the Grid. Alana knows where available computers are, and this information is updated live. The visitors can also learn where they can buy a cup of coffee or something to eat. And lastly, they can learn general information about the Grid building, such as the opening times and the construction date. With these functionalities, users can interleave multi-turn open domain conversation with task-based dialogues. I will now move to the part with the actual demo. The demonstration will be given using the Google Actions console. Hey Google, talk to Alana chatbot.
Let's get the test version of Alana chatbot. Hello, welcome to the Grid building. I am Alana. What can I help you with?
What is on today?
The Grid is a busy place. Today there are 29 events happening across 13 different rooms. For more details, you can ask me what events are on in a specific room.
What is happening in the creative studio?
There is one event taking place in the Creative Studio today. An event called Computer Games Programming Workshop is scheduled from 16:15 until 18:15. Can I help you with anything else?
Yes. Is there any news about Manchester United?
So I read an article about Manchester United on Business Insider with the title, Manchester United reportedly pulled out of a $24 million deal for one of Europe's hottest young strikers because it didn't want to give his father an agent a cut in his future sale. Do you want to hear more about this?
Yes, that's interesting.
I'm glad that you are interested in this news story. I was reading that Manchester United missed out on the signing of Erling Braut Haaland because of monetary demands made by his father and agent, according to The Guardian. Let's chat more about this.
Who is Erling Braut Haaland?
I believe that according to Wikipedia, Erling Braut Haaland is a Norwegian professional footballer who plays as a striker for German Bundesliga club Borussia Dortmund and the Norway national team. A prolific goalscorer, he is recognized for his explosive acceleration and pace, athleticism, strength and precise off-the-ball movement.
How old is he?
Right, Erling Braut Haaland is 19 years old. He was born on July 21, 2000.
Okay, thanks. I need a computer. Are there any free PCs in the Flex Lab?
Sorry, there is Flex Lab 1 and Flex Lab 2 in this building. Which one do you mean?
Number 1.
I'm afraid there are no free computers in the Flex Lab 1 at the moment, but I know that the Room Digital Lab has the most free computers. It has 68 PCs available. Can I help you with anything else?
How do I get to the Digital Lab?
Would you like to take the stairs or the accessible lift?
I prefer the stairs.
From the entrance, head across the atrium and take the stairs. At the top, turn left. The door to the digital lab will be in front of you. Let me know if I can help you with anything else.
Actually, I could really use a cup of coffee.
You can have a coffee, tea, or even a smoothie at the cafe on the ground floor. What else would you like to know?
What time do you close?
This building never closes. It is open 24/7. What else would you like to know?
That's all, thanks. Bye.
It was lovely talking to you. Bye.
Thank you for your attention and have a nice day.
Hello, my name is Thilo Michael from the Quality and Usability Lab from the Technische Universität Berlin in Germany. And now I'm going to showcase you Retico, which is an incremental framework for spoken dialogue systems. So let me give you a brief overview. Retico is a Python framework to create spoken dialogue systems and spoken interactive systems in general. It implements the concepts of incremental processing, has a simple API to connect networks of modules, has a graphical user interface that runs in the browser, and is documented, and the code is extendable. The whole package is available open source on GitHub. First, let me give you a quick introduction into incremental processing. Usually, dialog systems are structured in a pipeline fashion, where there are different modules connected together, and each module has a separate task. For example, a speech recognition module recognizes speech and transforms it into text, and then forwards a whole sentence to another module, for example, a natural language understanding module, which then tries to extract meaning from that. In this type of system, each module processes a whole input sequence, for example, a complete sentence, before forwarding the information to the next module. However, this is very inefficient because the modules need the information from the preceding module to get to work. Incremental processing is a concept described by Schlangen and Skanse in 2011 that describes a concept where information is transmitted as small increments called incremental units. So each module does not wait until the whole input is complete to forward the information, but rather forwards small increments and hypotheses. Let me give you a quick example. In this case, on the bottom we have an automatic speech recognition, and at the top we have a natural language understanding unit. Here we can see that the automatic speech recognition updates only the information that has changed to the last step. And we can also see that the natural language understanding unit is able to create predictions and hypotheses from the unfinished data and later revise those predictions to make them more accurate. This way, modules later on in the pipeline can create early hypotheses and start processing earlier. Retico provides an environment for incremental networks and provides interfaces with which modules can interact. It has already built-in modules for handling basic audio and text processing, and it also comes with several state-of-the-art modules like Rasa natural language understanding and Google's speech synthesis and speech recognition. Now I will give you an overview over the Retico API and the graphical user interface, and I will also showcase two services that are built with Retico. One is a translation service, and the other one is a simple spoken dialogue system. Let me show you the Retico API. Here I've imported three modules. The microphone module that is able to collect information from a microphone. The Google ASR module that takes in speech and transforms it into text by using the Google ASR API. And a callback module that lets me output any information I want. So first I create the modules. Here I created a microphone module with a buffer of 5,000 bytes. Now I'm going to create the speech recognition module. Next, I'm going to create the callback that just prints out whatever it is receiving. Now that we set up the three modules, it's time to connect them. First, let me connect the output of the microphone to the input of the automatic speech recognition module. Next, I'm going to connect the output of the speech recognition to the callback module. And lastly, I call run on all the modules so that they start working. With this input statement, the program waits until I press a key, and after that, let's stop all the modules. And those are the basic blocks on how to build networks with the Retico API. If I now run this Python script, we can see that the microphone starts working, the Google ASR transcribes everything I say, and the callback module outputs the text. With this API, it is easy to create own modules and connect them with already existing ones. However, in larger networks, it can be difficult to maintain an overview over all the modules and connections. So there is a Retico graphical user interface with which you can create modules and connect them. This is the Retico graphical user interface, where you can place modules on a canvas and connect them. On the right, you can see all the modules that are available and can be placed on the canvas. On the bottom, you can see networks that were saved to a file and can be loaded. Let me quickly build a translation service. For the translation service, we need a microphone module, a speech recognition module, a translation module, a text-to-speech module, and a speaker module. Let me place them on the canvas. Now that I placed all the modules on the canvas, I can move them, resize them, and enable and disable them. Let me now arrange the modules. Now that I have arranged the modules the way I like them, I can connect them. For this, I can use the input and output buttons. Whenever I click a button, for example, if I take the output of the microphone module, the modules that can take the output of the microphone module as an input, I highlight it. So I connect the microphone module to the Google ASR module, and now I will connect the rest of the modules. And now we see the complete network. The microphone module takes its outputs and gives it to the Google ASR module, which recognizes German language. Then the text is forwarded to the translation module that transforms German text into English text. Then we have a ASR to TTS module here that transforms the incremental units from the translation to the speech synthesis. The speech synthesis itself takes in English text. And then we have an audio dispatching and streaming speaker module that take care of outputting the audio. When I now click Run, we can see that the module is translating everything I say. Viele Grüße aus Deutschland.
Greetings from Germany.
Let me now show you a simple spoken dialogue system. I already built this network, so I can use the load function of the graphical user interface to load the spoken dialogue system. As we can see here, the spoken dialogue system is very simple. It takes in the microphone input, uses Google ASR for speech recognition, it uses Rasa's NLU for natural language understanding, and passes the information to a dialog manager. This is just a simple rule-based dialog manager. This end of utterance module uses the information provided by Google ASR to determine the end of the utterance. The dialog manager outputs text, which is transformed into speech by Google TTS, and then again an audio dispatching and streaming speaker module take care of outputting the speech. If I now click Run, I can interact with the spoken dialogue system and ask it for restaurant information. Hello.
Hello, I can help you find a restaurant.
I'm searching for a cheap Italian restaurant.
Okay, where would you like to eat?
I would like to eat in the north of the town.
Okay, you want to eat cheap Italian food in the north of the town, correct?
Yes, that's correct.
I have the following restaurant for you, the generic restaurant at Main Street 123.
During the execution of the network, the graphic user interface shows information about the current status of each module. And as you could see, the information was processed incrementally. Because the graphical user interface uses the same API I showed you earlier, we can save this network to a file and then go into our Python editor, and there we can load this network. Now all the modules and their connections into these Python objects, and I can iterate over them and start them. When I now run the script, I can interact with the spoken dialogue system. Hello.
Hello, I can help you find a restaurant.
This was a short overview over the Retico framework. Thank you for your attention. If you want to check out the GitHub repository, the link is on the screen, and if you have any questions, please feel free to ask me.
Hi, I'm Arne, and today I will talk about MCSA Instruct, a platform for Minecraft instruction-giving agents. This is a platform for experimenting with situated instruction-giving agents, and in general we would be interested in having them work in the real world. But performing experiments in the real world is prohibitively costly and nearly impossible, because we would need really well working computer vision, action detection, object tracking, and so on. And people in the real world have an unlimited action space. Therefore, we use a virtual environment. There has been previous work with virtual environments, for example, the GIF challenge, and they used custom-made virtual environments. This has two drawbacks. So, for example, in the GIF challenge, a user had to navigate several rooms and would be instructed to press a specific button in one of the rooms. It is very time intensive to develop these environments, and once you have the environment, it is hard to adapt this environment to a new task. So for example, if you want to have a building instruction in GIF, you would essentially need to rewrite all your environment code. We therefore use Minecraft for experiments. Minecraft is a single and multiplayer 3D sandbox game. It is the most sold computer game ever, focusing on building and exploration. There are millions of videos about Minecraft available online, so we can see how humans interact with Minecraft and how humans do instruction videos with Minecraft. And we can run our own servers. That means we can host Minecraft servers for our experiments. And now I will show you how such a server looks like from the user perspective for our experiments. The user simply uses the stock Minecraft client, selects a multiplayer game, then only has to enter our Minecraft server host name, which you can also if you want to later on. And then upon successful connection, the player is teleported into their own world. In this world, the player can build and move around, and the system observes all these actions and gives instructions based on these actions. Behind the scenes, we have several components. First of all, we have the Minecraft client running on the user's machine. The client connects to our Minecraft server. The Minecraft server, again, is connected to a broker, which is the centerpiece of our infrastructure. The broker is responsible for logging everything that happens during the experiments, and it also performs matchmaking between the Minecraft client and architects. Architects can be of different types. They instruct the user, and for example, in an experiment, you could compare a dumb architect to a sophisticated architect. In that case, you would have two different architect servers, and both architect servers would host one type of architect, and then each architect will correspond to one player and instruct the player. And only the architect is specific to the experiment, and all the other components are unchanged when you create a new experiment. Let's look into these in more detail. The first component is the Minecraft server. We use the official Minecraft server patched with the patches from the paper Minecraft project, which allows to use additional plugins. We have a plugin which initializes the player world and forwards all information between the Minecraft client and the broker. So from the Minecraft client, it forwards all player actions, and from the broker, it forwards the instructions back to the player. Then we have the broker, which routes and stores all data. Whenever a new user logs in, it selects what scenario to use. For example, you could have different scenarios that need instruction, such as building a bridge or building a house, and which architect this user should be connected to. For example, the dumb architect or the sophisticated architect. And optionally, it can also run the post-experiment questionnaire, which means that all your experiments can run in Minecraft without any external tools. This post-experiment questionnaire is done in the Minecraft text chat. Then we have the architect server. The architect server hosts all architects of a single type. It instantiates architects per game via factory methods, performs routing to the correct architect, and every architect implements a simple interface. The first method of this interface is called every 10 milliseconds with the current position and orientation of the player. The second one is called whenever a block was placed. The third one whenever a block was destroyed. And the last one simply returns the name of the architect so that we know what architect was used for an experiment. The architect has access to a send message method, which is used to send instructions to the user. And the architect server and broker take care of all the routing for this message. And the architect does not need to care about the existence of several users on the same server. Technology-wise, everything is written in Java, including the Minecraft server. We use gRPC for high-performance message passing. That means that if you want to use a language other than Java for your architects, you can implement them in any language you want, as long as there are gRPC bindings, and every major programming language has gRPC bindings. And lastly, we have a block list for users, and every user is added to the block list after the first login. That means that no user will be able to participate in your experiment twice. Other than that, we also have shell scripts to automate installation, setup, and start, which you can see on the bottom right. And these automate everything for you. And they are structured in a way to make it easy to extend this in case you want to run your own experiments. We have a web interface showing the status of the broker and also the currently running games, and for every game in the database, all events that happened, and you can filter them, and this is really handy for debugging reasons. So to conclude, Colizar Instruct is an adaptable framework for situated instruction giving. It can be expanded to text-based situated dialogue, where users also write text. It abstracts away all the unpleasant low-level stuff, so you do not have to care about all this. It taps into a huge Minecraft player base, and it is already proven to work really well in first experiments. And it is really fantastic to see how fast you can get players to play with your system. And you can see all our resources on our website. Thank you very much.
This talk introduces ConvoKit, a new Python toolkit for analyzing conversational data. Conversations are quite diverse, ranging from online conversations like social media to offline conversations, both institutional and informal, and even to fictional conversations like movie scripts. So clearly, conversations can vary wildly in terms of the contexts, settings, and formats that they take place in. And yet, despite this diversity, there are also some key unifying properties that are shared by all conversations. One such unifying property is that conversations are structured. That is, the utterances in a conversation cannot be treated as standalone documents. Instead, we must also consider how they relate to each other. For example, who replies to who and when replies are uttered. Second, conversations are inherently social. That is, the interpretation of a conversation depends on the people within it. For example, an utterance that might be considered rude by one audience might be unobjectionable to a different audience. Unfortunately, the current state of conversational data does not directly reflect these key unifying properties, and this can pose barriers to running the kinds of interesting analyses that we as scientists who study and model conversations might want to do. To see why, let's consider some concrete examples. One problem that immediately arises is that there is no universal standard for how conversational data should be represented. As such, some datasets are formatted as simple CSV tables, while others can take on a more complicated format, like this list of JSON objects. This poses challenges to generalizability, as code written to analyze one dataset may need to be heavily rewritten to analyze a different dataset. Furthermore, limitations of these text-based formats restrict the extent to which they can represent the rich structure that conversations have. Of course, datasets often provide pointers to reconstruct that structure, such as the ID and parent ID fields in this JSON object. However, actually using this data to reconstruct the structure can require writing quite a bit of boilerplate code, which takes time away from the actual analyses that we are interested in. As such, it appears that there are two missing ingredients needed to streamline conversational data analysis. First, we need a unified representation of conversational data, and second, we need a general language to describe manipulations of that data. Providing both of these missing ingredients is exactly what Convokit aims to do. Now, let's look in more detail at how Convokit achieves this.
So what does this unified representation look like? Well, intuitively, conversations or discussions between some group of people are simply some sequence of utterances where each utterance is made by some speaker. And so in Convokit, we represent conversational data using these three concepts: conversations, utterances, and speakers. And each of them are first-class data objects in Convokit. A collection of these components is what we call a corpus, which basically represents the entire conversational dataset. Now, as first-class data objects, each of these components shares a consistent data format. Each of them has some set of primary data fields, such as ID, and each object has its own metadata, which is where we will encode additional data attributes, such as predictive features and labels. Now, one really nice thing about the Convokit hierarchy is that the data objects are interoperable, meaning it's easy to navigate from any one component to any one of the other two components. And so it's easy to do higher level analyses, like track a speaker's behavior across all the conversations that they've participated in their lifetime, or characterize a conversation by the composition of its utterances or the speakers that have participated in it. In addition, each of these objects have their own methods and functions, which makes them really powerful for all sorts of analyses. So for example, we discussed the problem of encoding conversation structure. Well, in Convokit, conversation structure is automatically encoded, such that for every conversation object, you can automatically access its structure and even traverse the conversation tree in interesting ways, like a breadth-first or depth-first traversal. So now that we have these data objects, the question is, how do we do higher level analysis with them? And so now we introduce the concept of a transformer, which at a high level takes in a corpus and applies some sort of transformation or modification to it. And these modifications usually come in the form of changed or added metadata for one of the corpus components, meaning its utterances, speakers, or conversations. Now broadly, these transformations come under three categories: preprocessing, feature extraction, and analyses. And we now quickly run through a few examples of each of these. So for preprocessing, for example, you might use our text parser transformer to annotate the utterances within the corpus with their dependency parsers. You might use the text cleaner transformer to lowercase and remove any Unicode from the text for all the utterances within the corpus. For feature extraction, you could use something like hyperconv, which represents conversations as graphs and computes graph-related statistics, and then annotates the conversations with these statistics. Or if your corpus already has dependency parsers for its utterances, you could build on it by using politeness strategies, which uses these parsers to identify linguistic devices that indicate politeness. Finally, for analysis, you can use something simple like ranker, which lets you rank some of your corpus components according to some arbitrarily defined metric. For example, you might rank your speakers by the number of utterances that they've made. A more complicated example would be classifier, which lets you train any scikit-learn predictive model using the predictive features of one of your corpus components, such as the politeness strategies of your utterances. Now, all transformers are inspired by and conceptually analogous to scikit-learn's own transformers. And they each have a fit step, where you might train or fit some sort of internal model, a transform step, which does the modification of the corpus that we've just described, and a summarize step, which usually summarizes the modifications that have been made to the corpus in some sort of visually interpretable way. And because each of these transformers have a fit transform paradigm, you can combine them in sequence for more complex operations. And so using the examples we just described, you could set up a pre-processing, feature extraction, and analysis pipeline very easily simply by chaining these transformers together. And we even have a convocate pipeline class to facilitate such pipeline analysis. We now move on to a concrete application of convocate, where we examine differences in language in fictional conversations. And here we use movie corpus, a corpus of movie transcripts. And one question that might come to mind is, how do conversations that involve both male and female speakers differ from conversations that involve only male or only female speakers? And for convenience, we refer to these as mixed gender and single gender conversations. And so you might imagine some sort of analysis where we take utterances from both of these groups and then seek to identify salient linguistic differences between these two groups. To do this, we'll use an established method called fighting words, which is also available in Convocate. At this point, we're going to make two notes. Firstly, this is an especially interesting analysis because it uses all three levels of the Convocate hierarchy, namely conversations, utterances, and speakers. Secondly, a more rigorous analysis can be done with a more nuanced approach to gender, but because of the limitations of the movie corpus, which has only male and female labels, we are limiting our analysis to male and female speakers. So what does this look like as actual code? Well, firstly, we will have to load the corpus. We will use the text cleaner transformer to clean the utterances. And then we do some custom feature extraction, where we label conversations as mixed or single gender. And here we want to emphasize one of the virtues of Convocate, which is that it's easy to link components together. And so it's very easy for us to label this conversation based on the attributes of the speakers that have participated in this conversation, which might be more difficult to do in other setups. Finally, we do some fighting words analysis based on these two groupings and find a summary of language differences. And so all these steps comes down to a quick and simple 10 lines of code. And we're happy to run through this example in detail during our live Q&A. This demo is available online in our GitHub repository along with many other examples. In any case, if we run this code, we get this plot, which is very suggestive of differences between these two groups of utterances. We see that mixed gender conversations have more terms of endearment, like love and honey, or single gender conversations have more male terms of reference, like man, sir, and mister, which perhaps reflects certain known stereotypes that have been discussed in prior work, such as that mixed gender conversations tend to be more romantic in nature, while single gender conversations tend to be primarily between male characters. And so we want to emphasize that it's really quick and easy to set up these sorts of analyses in Convocate. And being able to so quickly generate an initial plot like this might be a useful starting point for more rigorous analysis. Through Convocate, we've offered a unified representation of conversational data, as well as a general language to describe manipulations of that data through transformers. In addition, we also offer a large and diverse collection of datasets already in Convocate format that come with rich metadata and are from a wide variety of conversational settings. Finally, our work is open source and we definitely welcome any contributions you may have. In particular, if you have any conversational datasets and methods that you'd like to share with the world, we're happy to work with you to incorporate them into Convocate. If you have any other questions or if you'd like to see Convocate in action, please join us for our live Q&A. Thank you.
Hello.
Hello everyone, this is Ye from University of Illinois at Chicago. Today I will represent our paper, Commonsense Evidence Generation and Injection in Reading Comprehension. Despite the great success of large pre-trained models such as BERT GPT-2, recent studies suggest that those models fail to capture sufficient knowledge and provide common sense inference. In this paragraph example, the man said he was walking home from the store. He saw an old man lying on the sidewalk, bleeding. The right side of his face was covered in blood, and nearby there was a young man dialoguing his cell phone. The question asks, what may happen after the young man makes his call? It's hard to answer this question based on the paragraph, but if the model could be provided by the evidence, like the young man will call for medical attention, or the factual evidence, both the blood and ambulance is located at hospital, it will help the model to select the answer A as the correct answer. To solve this problem, we propose data which generates useful evidence and inject generated evidence into pre-trained model. Since context itself often doesn't provide enough clue to get us to the correct answer, which means we need to know comprehensive information beyond the context and perform confidence reasoning. Here we split the text into two parts, evidence generation and answer prediction, respectively. We propose two generators, factual evidence generator and text evidence generator. In the text evidence generator, we rely on the pre-trained language model to report the textual evidence. Specifically, we state paragraph, question, and different options as input to train the language model. We train the model based on the language model laws. Moreover, we aim to generate evidence that can discriminate the correct answer from option distractors. Therefore, we add answer prediction laws and train the model as a multitask learner. In the test stage, we set paragraph and question as input to the language model and use the model to generate the next sentence as evidence, which means the model is agnostic to the correct answer. We utilize a factual knowledge graph to extract facts and relation and use them as additional evidence, and we call it as a factual evidence generator. Specifically, we use ConceptNet as a base knowledge graph and language model as a knowledge graph completion model to build new relations. To generate fact evidence, we first extract the source entity from the paragraph and question. Then we select the relevant and non-trivial tuple using graph filter method. Finally, we convert the filtered tuple into a natural language sentence as our fact evidence. After relevant fact reasoning evidence are generated, we combine the evidence with the given data and build a reasoning model to make a selector for the correct answer. We use Robota as an intermediate component to generate hidden representation of paragraph, question, option, and evidence, and use attention between different components and inject the evidence into the model. To incorporate the relation information, we use the co-matching algorithm to generate the relation representation between paragraph and other options. Then we concatenate all the pairs regarding paragraph, which is final representation of paragraph. Accordingly, we obtain the question and option respectively. We process the different option pair in the parallel, and we concatenate the M option as the tensor F. Since the final representation only contains the fine-grained token level information, we employ a convolution neural network to extract factual level patterns. In some situations, the candidate option set contains distractors that are quite similar to the correct answer. In other words, understanding the relation among the option set is also important. Therefore, we employ a capsule network which use routing by agreement mechanism to capture the correlation among different options and make the final decision. We test our model on the Cosmos QA dataset, which designed for reading comprehension with Commonsense reasoning. The data is sampled from people's daily narratives and types of questions concerning the cause and effects of events. The dataset contains 25.2 thousand multi-choice questions. We compare all the baselines. Our proposed model, SIGDIAL, use both text and fact evidence, has a highest accuracy on both development and test set. The baseline was split into 3 groups. In the first group, there's the reading comprehension approach, which utilizes attention mechanism to capture the correlation between paragraph, question, and option set. However, more than 33% of the correct answers are not in the given passage in the Cosmos QA dataset. Therefore, those models do not gain big improve as they tend to select the choice which has the most overlap word with the paragraph without Commonsense reasoning. In the second group, Commonsense KB and K-adapter teach pre-trained models with Commonsense reasoning. Those approach leverage the structured knowledge but fail to produce a permanent prediction improve. Compare our SIGDIAL approach with Robota, we gain 4% increase and 4% increase than K-adapter, which demonstrates that injecting evidence is beneficial and incorporating interactive capsule network can further enhance the model. We also evaluate the performance of 2 projectors. In the text evidence injector, we first pre-train the model on the large corpus open-man Commonsense dataset using language model laws, and then fine-tune the generator on Cosmos QA using the multi-task learning we mentioned in the above. For the result, we can see that both SIGDIAL BERT and SIGDIAL GPT-2 has high quality and diversity score, which implement that generated evidence are semantically consistent with the correct evidence and can be used as additional knowledge for the reasoning step. In the fact evidence generator, we observed that GPT-2 has the lowest perplexity and highest score, which indicates that SIGDIAL GPT-2 model is confident and accurate as generative relation. Since our proposed SIGDIAL GPT-2 and SIGDIAL BERT model has high score and low perplexity, we believe that both models can produce high quality knowledge and still be able to extend the size of the knowledge graph. We also show the case study of the 2 generators. In the first example, we show the text generator by the SIGDIAL robot. The evidence I will not have experienced the feeling that I have for her is close for the answer D. And in the second example, for the factual evidence generate, we know that B is capable of sting, so option C, because he got sting before, well be the correct answer. Some option like B appear in the context. I told him that most of plant animal life will be died within a decade of bee disappearing from the plant, and thus, without the evidence, it could plus the model to select the choice B. And for the case study of capsule network, it's hard to answer the question simply by reading through the paragraph. But since using the capsule network, which considering all other candidate options when answering the question, it can help the model to predict she wants her to look at the pretty rock as the answer. And it's all my presentation, and thank you for your listening. If you have any question, you can reach out to me.
Hi everyone, today I'm going to be talking about our work identifying collaborative conversations using latent discourse behaviors. My name is Ayush Jain, and this is joint work with Maria Pacheco, Stephen Lancet, Mehe Goendani, and Dan Goldwasser in Department of Computer Science at Purdue University. Just to give a brief motivation about a problem, as you all know, there's massive amounts of online conversations on platforms like Reddit, Yahoo, etc. And we as humans intuitively decide if a conversation is good or bad based on high-level discourse behaviors. These hidden behaviors are crucial in making the final decision about any conversation. In recent years, many efforts have focused towards identifying and filtering negative and abusive content and looking at the outcomes of such conversations. But our focus is on characterizing and automatically identifying the positive aspects of social interactions, specifically collaborative conversations. Let's consider a sample conversation. In this conversation, user A says we should invest in more resources to encourage young people to be responsible citizens. Now there can be two possible responses to the user A's post. First, I wonder if more initiatives at grassroots level can help them to identify and understand issues of the local community more deeply. Second response, good point, I agree. Now which one of these options is a better response to user A's post? Despite the positive sentiment in response to this no idea development and no balanced content contribution as seen in response 1, which allows us to infer that it's not a collaborative conversation. It's very easy for us as humans to identify such characteristics of a conversation. So we designed a hybrid relational model that combines neural networks and declarative inference to capture these high-level discourse behaviors and use them to identify collaborativeness in a conversation. We model these discourse behaviors as discrete latent variables that add inductive bias and constrain the representation learned by the neural model. It also provides a natural way to debug the learning process by evaluating the activation or deactivation of latent variables. Some of the challenges involved are that there are a lot of nuances involved in a conversation, and using such direct features can lead to conflicting information in identifying collaborative behavior in a neutral conversation. For example, presence of many disagreement markers in multiple posts as direct features can misclassify the conversation as non-collaborative, but the conversation can be a healthy discussion with flow of ideas. In order to define the task, we identified several repeating behaviors that help us characterize and define collaborativeness in a conversation. We build on the work of Nepos et al., who released a Yahoo Conversations dataset, which was originally annotated for engaging, respectful, and informative conversations, and we re-annotated it for collaborative conversation. We developed annotation guidelines and operationalized the indicators used to label a conversation as collaborative or not, resulting in an accuracy in inter-annotator agreement of 81% between the two annotators. Some of the collaborative behaviors that were found are high idea development, reference to the previous post, back and forth, positive sentiment, high user engagement, balanced content distribution, questions asked by the participants, etc. Some of the non-collaborative behaviors that were found were low idea development, low user engagement, negative sentiment, rudeness, and so on. To briefly describe the model, we view this classification task as a probabilistic reasoning process over the relevant conversational behaviors that were identified during the annotation process. Since these behaviors are not directly observed and have to be inferred from the raw features, we treat them as discrete latent variables which have to be consistent with the final decision. To learn this model, we extend DRail, a recently introduced framework for combining declarative inference with neural networks. The model consists of a set of predicates representing a latent or a decision variable. Here on the left side, you see a factor graph showing H1, H2, H3 as latent latent binary variables jointly connected with the Y outcome variable describing a conversation as collaborative or not. On the right side, you see all the rules describing the discourse behaviors as well as the mapping of discourse behaviors to the outcome variable. Various structural, content, and user-based relevant features are used for each discourse behavior, and each of these rules has an associated neural network that is used to learn parameters of a scoring function that is used to enable or disable that behavior. These kind of rules enable both the expressivity and interpretability of the relational model. Talking about learning and inference in derail, derail learns a globally normalized model which uses inference to ensure that the scoring functions for all the rules result in a globally consistent decision. The model uses structured hinge laws as shown on the left, which is used to handle latent predicates which is defined over all the neural parameters W, and the error is backpropagated to update all the networks. Here, epsilon is a slack variable capturing the margin violation penalty for each training example xi, having a gold label yi, and h on the right side refers to all the activations for discourse behaviors. For inference, derail uses integer linear programming by finding optimally scored assignments of output values to the variables. Talking about the model evaluation, specific details about experimental setup and dataset can be found in the paper, but the main results are as follows. We compare our derail global model with 3 other models, derail local model and variants of linear SVM model. The derail global model consists of all the latent variables rules and the mapping of latent variables rules to the final conversation outcome. The derail local model consists of a single rule mapping the raw conversational features directly to the outcome of a conversation. The linear SVM and other variant consists of bag of words features and bag of words features along with discourse features. We clearly see that the derail global model outperforms the other 3 models by a large margin, as seen on the left. We also try to evaluate the quality of the predicted latent behavior in our model by annotating a small set and trying to see the performance on that set before and after the global training. As seen on the right, the performance of each behavior consistently improves after the global training. We also performed feature ablation study and saw that rules related to idea flow, sentiment, and balanced content behavior leads to an inference score of 0.62, which means that these 3 behaviors are crucial in determining the collaborativeness in a conversation. To conclude, this model can be easily extended to accommodate more nuanced discourse behaviors, and capturing such complex behaviors almost perfectly and their dependencies allow us to make global prediction about various kinds of decisions, including collaborativeness as shown in this work. Thank you.
IVAs are a specialized subset of chatbots designed to mimic human customer service agents for commercial enterprises. But because enterprises are more protective of their data, sharing research becomes more complicated. There are interesting features that are unique to the language in this domain, so we present a framework that allows the research community to understand how this language is unique when compared to human communication in the same domain. For this study, we are not looking at purpose of use, we are only looking at language features. One of the unique advantages that we had was live chat and IVA data from the same client for the same purposes. We also were able to look at the effect that the IVA had on human-to-human chat language after an IVA conversation. One of the primary success metrics for this IVA was live chat deflection. If the IVA is able to handle the frequent and easy issues, it will free up human live chat agents to handle the more difficult issues in a more timely manner. The live chat data used in this study was also used for the initial training of the language model. Because a user is still able to go to live chat when requested or when business rules required it, we allowed for substantial time to expand use cases and refine the language model to allow for a best case comparison. For the IVA implementation in this study, There is no attempt to make the IVA appear human. There's no avatar. The initial message states that it's an IVA, and there is a nominal static delay as the immediate response reportedly felt uncomfortable to those who were in charge of user experience. Also, currently, there is no way to live chat without interacting with the IVA first. This is a reflection of the success of the implementation in meeting the quality goals of the IVA. At the conversation level, we see how much more efficient an IVA conversation is. Live chat takes 1.7 times more turns and 2.5 times more words. Also, we see that there is some impact on the live chat conversations after already having chatted with an IVA. There are more turns than live chat alone and more words in the conversation. The live chat agents are given the IVA conversation, so we believe that the live chat agent may not be using the IVA conversation as a contribution to this new conversation. Looking at the turns themselves, we see the turns are between 1.5 and 1.8 times shorter with an IVA, but not only are users being more concise, they're also being substantially more careful as demonstrated by the misspelling data. It also turns out that IVA users feel no meaningful need to express gratitude or meaningful sentiment to an IVA. One of the major concerns in implementing an IVA is the human impact in live chat centers. While we do see less gratitude offered to live chat agents, which is probably representative of the more difficult conversations, sentiment scores are not significantly impacted. For syntactic complexity, we see numbers consistent with shorter IVA inputs. However, there are two metrics that stood out: complex nominals per t-unit and mean length of clauses. This may indicate a tendency of IVA users to rely on conveying information through noun phrases more than complete verb phrases. However, these increases were not reflected in users who escalated to live chat, and the reason for this is unclear. Live chat data is measurably not representative of IVA data. Training and testing language models using raw live chat data is not recommended. However, live chat data can be curated to be representative by selecting the shorter, more direct language that is present there. Where there is no live chat data, we recommend a data collection strategy that is relevant to an IVA task instead of paraphrasing strategies or restatement strategies or relying on other open human-to-human data sources. IVAs can be great for users. An IVA can always be available instead of forcing a user to wait for the next available human to respond, and a user can accomplish a task more quickly and efficiently than communicating with a live chat agent. However, there may be a negative impact to the people in the call center. The conversations that they're dealing with will be more difficult, leading to longer conversation times and less opportunity for easy resolutions and therefore easy positive feedback. The traditional success metrics for these positions will need to be adjusted to accommodate this new situation. Thank you.
It's all you, Dan. Go ahead and take over, and we can, of course, wait for more people to join.
Thanks, Casey. Hey guys, hi, yeah, Timothy and Ayush. Casey, should we, I guess we can wait until the session is supposed to start at 11:20. I want to make sure I give people a chance that are clicking on that link at 11:20 to join in, maybe before we start, if that's okay.
Yep, absolutely. Let's go with the schedule.
Hey guys, so I guess maybe we can get going. It's 11:20. I wanted to give a few more people a chance to join in, but we already have some people in the room. I guess more might trickle in. So my name is Dan Bohush. I'm at Microsoft Research. I'm going to be chairing this live QA session. The session is entitled Knowledge Acquisition, Use and Behavior Modeling. And I think we just watched 3 different talks. What I'd like to do is first, I will thank the authors for the great talks, for the recordings. We're all getting used to this new way of doing things. But it was great to watch those talks. I think we have about 20 minutes. So let's try to maybe allocate the same amount of time to each paper. We'll start from the first one. And if there's not enough questions for a paper to fill that time, we can keep going and then we can come around all the way back, or we can open up for any questions to any paper. So I'd like to start with questions for the first paper that was Common Sense Evidence Generation and Injection in Reading Comprehension. I think we have Ye on the call to answer the questions. So does anyone have any questions? I'm not sure I see any hand raised here. Casey, I assume you'll help me if you notice someone raising their hand. I'm still getting used to this interface, but
yeah, I'll help you. I don't see anyone either.
If there are no questions, I would like to ask a question. So you mentioned in one of your tables, you show how the model that you build, improved upon other kinds of models. I think I remember at some point there was some results around like, 83% versus, previous 79%. So you've got some improvement. I was curious if you've done an error analysis. Like, does the motivation was great, right? Like the idea is that bringing this factual evidence, can improve the models. I was curious, are the errors that this model commits now similar to the errors that the previous model does? Are they complementary? Have you looked in any way at the errors that this model commits versus the previous model and see if the factual stuff helps?
That's a good question. Actually, I didn't look at all the questions have the error, whether they're similar with the previous. But I can see our model can solve some problem, like the previous model that doesn't provide the evidence to help the model to answer the question. So that kind of question, our model can deal with that problem. But I didn't check about other case of the error, whether our model can solve that kind of problem.
I see. That might be something interesting, I guess, for future work. I think it's always interesting to see kind of like where, what the model resolves and whether, because if the errors are a bit complementary, if they're not the same, you might hope to improve by somehow leveraging the models together and so on. I had another really quick clarification question. I didn't quite exactly follow. So you had this factual evidence generator. I understood how you took ConceptNet, managed to filter a bunch of triplets. How did you go? You said that from there you went to natural language sentences, like you generated natural language sentences from the triplets. Was that based on some templates, or how did you do that generation?
So the triple is kind of, they can easily using some rule-based method to translate to the natural language.
I see. And the rules were general regardless of the kinds of objects? Like how many rules? I'm just trying to get a sense of like, did you manually author these rules or?
Yeah, it's not too much, like just less than 20 kind of category of the relation tab. So just not too much rules do that.
I see. Okay. Okay, well, I want to make sure if there's someone else that has questions, they get a chance to ask. Do we have any other question for you? No, I don't see any other question yet. So let's move on to the next paper, and then we'll open the floor back to all papers at the end. So the second paper we saw was identifying collaborative conversations using latent discourse behaviors. And I think Ayush is, hi Ayush, is online with us here. So any questions for Ayush? I guess I'm not seeing any hands raised. So I found the paper really interesting, and the presentation. I had some some questions about the understanding a bit better the factor model and how you came up with you enumerated the list of discourse behaviors.
Right.
I'm just curious if you could say a bit more about how you came up with that set. Do you feel it's kind of complete in any sense, like, you know, or do you feel like there could be other kinds of discourse behavior? Is there a principle there or a taxonomy of sorts?
Right.
How did that come into being?
So I guess the main inspiration for the behaviors that we enumerated was from our annotation guidelines. Basically, the idea was that as per our definition of collaborativeness, we basically sampled few conversations, like 50 to 100 conversations, and then just try to see like what are the behaviors that we as humans intuitively decide that makes it collaborative. And once we came up like different high level behaviors, we basically tried to capture those through the rules that we have. And the idea was that whatever rules that we come up with, they have to be like the features for them have to be like sort of exclusive in the sense that they don't overlap that much, so that we have a clear distinction between the discourse behaviors that we have, so that whenever we have to debug later on, like let's say why is this collaborative conversation and not a collaborative conversation, you can clearly know that this is the behavior that is being turned on, and which makes sense that the combination of these activated behaviors leads to a like a collaborative conversation or not. So the main inspiration was basically our like a human judgment of few sample conversations from the data set. But yeah, as you said, like it's definitely not an exhaustive set for sure, because it's only one data set. And maybe if we have like multiple data sets from different topics or themes, it can like increase the possibility of having those behaviors. But the best part is that the model can easily be extended by adding like just plugging in 2 more rules with their corresponding features, and then you can do the inference later on as well.
Got it.
Yeah.
Got it. That makes sense. Thanks.
No problem.
Other questions? Give people a chance.
Sure.
I have a couple more, but I want to make sure if there's someone else that wants to ask a question, that don't be shy, jump in. So raise your hand. So I will ask a couple of other questions. So with the factor model, if I understood correctly, that graph, were the factors that characterize the relationship between the behaviors and the target variable, like the collaborativeness of the conversation, were those like manually set? Were those also trained from data? Were they fixed form? Were there also deep nets or neural networks? Because I feel some of the other factors were neural networks, but it wasn't clear if all the factors were.
Yes, so all the factors that you see were trained as well, were learned. And the idea was that the final outcome variable can be trained directly from raw features as well, and as well as the high level binary latent variables that we had. So it's a combination of both.
So since those variables were binary and latent, like I'm trying to follow, like, were they labeled in any sense? Like during training, did you have labels? Or if not, how do you know which corresponds to which? Like, how do you do the assignment of this represents this behavior? Like if you just have a bunch of latent variables.
Right, so each of those rules has the separate mapping from that behavior to the outcome variable. So you know that this is the behavior that is being mapped to the outcome variable.
I see. So unless there's other questions, I have one last question, which is, could you clarify a bit the other part that I didn't quite, wasn't able to follow? You mentioned like you used ILP as part of this, and it wasn't clear to me in which part, like what role that played exactly. Can you describe that a bit more?
Right. So due to space constraints, I didn't have the equation to detail more about ILP. So the idea was that each of those activation or deactivation of latent variables will have another equation that basically constrains the activation or deactivation of variables. Let's say you have like a behavior that says that if you have like, for a hypothetical scenario, if you have activation of idea flow, then you have maybe not of rudeness or whatever behavior. So this becomes another constraint, and each of this behavior that you have is another variable there. So if you have like an equation that just does an argmax of Ri into the score of each of these variables, then you can basically plug it into just another ILP solver, which basically gives you all the possible activations and deactivations of those behaviors, basically allowing you to do infer about the behaviors
which ones are present. Yeah.
Exactly.
Okay. Got it.
Dan,
okay,
Emma
thanks.
Pacheco has a
yes,
comment.
I saw that comment.
Okay,
I saw that
great.
comment. So I'm asking him to unmute here. You can go ahead, Emma Pacheco.
Hello. Hi, I'm another of the authors of the paper. So I wanted to add to your question about the latent behaviors. So there is no supervision for those latent behaviors. So they're completely latent. The supervision that we have is for the collaborativeness of the conversation. What we did was kind of identify which are these variables that we would like to capture. So we gave them some definition and then see whether the features that we generated for them and the activations kind of correspond with the intuition that we have for these latent variables. And we annotated a subset and we're able to see that we correctly captured these things.
I see.
But there's no direct supervision for it.
I see. That makes sense. Makes sense. Cool. Thank you. Well, I don't have any other questions. So if someone else in the meeting has more questions for Ayush. I see also someone is in the waiting room. I'm gonna hit admit here, Alex. Okay, then let's move on to the third paper, which was basically a case study of user communication styles with customer service agents versus intelligent virtual agents. And I think we have Timothy online to answer questions that you guys might have. So does anyone have any questions? I will then go ahead and ask one question that I have, which is interesting to see. It's always interesting to see these studies, based on real data, in an actual center. There seem to be, if I understood, and correct me, I might have not misunderstood this correctly, but there seems to be almost like a confound here of the difficulty of the task that had to be solved, right? Like if the users initially go to the agent and only reach the human if the task gets more difficult, there's a difference, it seems, between those types of interactions, and you're detecting some of that. I was curious, do you think it would be feasible, or was it not feasible in your data, or do you think it's feasible in the future to do this kind of analysis without that confound, where you kind of, you flight a subset, like 5% of the users, and randomly assign them so that you can really compare more apples to apples? Or did I misunderstand something? It's possible I misunderstood something.
So this is about as apples to apples as we can really get. It's okay. The live chat and the IVA were both the same client, same purposes.
Right.
So everything that they're doing should have been the same. There's just a few examples where, like for canceling an account, that's not something that you want a chatbot to do. You want to give that to a human agent so that they can hopefully keep that account alive. You want somebody in sales to try to avoid that situation.
Got it. So I must have misunderstood, because I thought there was this situation where when the user would come into the system, they would first interact with the chatbot, and if that failed, then they went to the agent.
Yeah.
But that seems to imply that all the easy tasks, or some easy tasks, like the distribution of the nature of tasks, that the agents will handle and the people will handle, will vary in terms of their difficulty or how challenging it is, just because these are sequential.
Yeah.
And I was wondering, like, I guess in my mind, like, I'm not sure if this is possible in an actual context of a business that's running and doing this thing, live. Their interest is to get service done via the IVAs, I guess. But I was wondering if for a subset of the data, you could actually, the first time the user arrived, choose randomly whether you send them to the agent or you send them to the IVA instead of always sending them to the IVA first.
Maybe we could do that, but contracts wouldn't allow that.
Yeah, I see. So it's a business decision basically. And
yeah,
interesting. Okay, are there other questions for Timothy? We might be done a little bit early in that case. I don't have other questions, so unless I'm gonna give you guys one more chance. And also not just for Timothy, I should say, like for any of the other two papers, if someone has joined the meeting room not right from the start, if you have questions for Ye or Ayush or Timothy. Doesn't look that way. So Casey, I think then we're ending maybe a little bit early this session. I'm not sure what's next, whether we're going on a break or something else is starting.
I can answer that. Thank you, Dan. Thank you, everyone who participated. And thank you, authors. I really enjoyed the session. Dan, you can hear me okay? Okay, thank you. I'm going to share my screen yet again and kind of tell you what's happening next. We go from here, which we just finished session 3, and we go from here to the breakout discussion topics. Each session is 45 minutes to an hour, and there are 3 of them 3 of these scheduled in a row. So you can start with one of these 2. These 2 both happen in a little less than 10 minutes from now. You'll notice that there is a Zoom link or a Google Meet link. So if you click on one of these are the discussion topics that you can join. These 2 are happening, like I said, very soon. The next hour of breakout discussions that happen directly after that are these 2. So Real Dialogue Challenge and then the virtual conversational agents in the text channel. So feel free to join those as well. And then an hour after that, so these are all back-to-back, 3 sessions in a row, 2 for each session. The next session, starting at, well, at least for me, an hour, 2:45 p.m. Mountain Daylight Time, is dialogue management. And then in parallel will be emotion and expression in dialogue. There are some other ones for today, but those are going to be later. So right now it's these 6, 2 per hour. So we encourage you to join those. And then the next thing that follows after that will be a break. And then the last part of our day will be this special session, RoboDial 2.0. And that will start in a little bit more than 3 hours from now. So I'm going to end this live stream. I'm going to end this Zoom meeting, and that's going to be it. There's going to be no live streaming for the next 3+ hours. I encourage you to join whichever one of these or multiple ones of these that discussion groups that you would like to, and then meet us back here. I will post new links for the live YouTube for the Zoom meeting, and we will finish out day 1 with the RoboDial session. So thank you very much, and have a great open breakout discussion time.
Thank you.
Thanks, guys.